Our next speaker is Professor Antonio Bianchi. Antonio is an assistant professor of computer science. His research focus areas include IoT and mobile device security and novel approaches to analyze compiled binary code. He also serves as the academic advisor to the boilers, that would be B01LERS, the Cyber CTF competition team here at Purdue that has maintained a top 10 global ranking for the last several years. Was the defending national champion of the Raymond James Collegiate National Championship this last year. And members of that team competed in the Sandia National Labs Chaser Fire Cyber Defense competition this last week that won that championship. So in addition to being an unbelievable great researcher and educator, you're obviously an unbelievably great coach as well, Antonio. So it's all yours. We're excited to hear the very first technical talk of the symposium.
Hello.
Hi, Antonio. We can see your slides and we can hear you.
Can you hear me now?
Yes.
Okay, good. Very good. Okay.
It's a little quiet though.
Is it okay now?
I think we can hear you. Yes.
Okay.
Much better. Perfect. Thanks you, Antonio.
Okay, so today I'm going to present. So first of all, thank you for the introduction, and yeah, and I'm just going to present a work we have done recently together with, of course, students at Purdue, Jillian, Royu, and also professors and students at other universities, specifically at EPFL and CISPA in Europe. And so this work is called LightBlue, and the general idea is that we want to prevent attacks. We want to make the code safe, specifically the code dealing with Bluetooth stacks. And I guess everyone knows Bluetooth, and everyone has at least a few Bluetooth devices that are probably used every day, and the amount of Bluetooth devices is definitely increasing over the years. And one less obvious thing is that these Bluetooth devices, they support a lot of very different applications, going from the standard, Bluetooth headphones to more specific things like health devices that are connected through Bluetooth, or I don't know, printing or sharing connections and things like that. So there are a lot of different applications that you can use through Bluetooth. And in general, especially due to all these different Bluetooth applications and functionality, the Bluetooth code is bloated. So there is a lot of code that is typically unneeded. And going a little bit more technical, we can say that Bluetooth supports multiple profiles, and more or less each profile corresponds to one functionality. So here we have this one on top row, these are profiles. So we have GATT, we have HID, we have PAN, different profiles. Every profile then is using different protocols of different protocols, SDP, L2CAP. And then all these protocols, they generate what is called HID commands, and they send these commands to the firmware that is running on the controller. So to add complexity to this is the fact that the thing here you see on the top, those run on a standard CPU, typically, I don't know, your laptop CPU or your phone CPU, whereas the firmware here at the bottom runs on a separate CPU that is the CPU running the dedicated Bluetooth controller. And all of this code is a lot of code, is probably hundreds of thousands lines of code. And of course, it's it towards the years, people have found a lot of bugs into this code. And so here I'm just highlighting the host code and the firmware code. But in a lot of cases, we are not really interested in all of this code. A lot of Bluetooth applications and use cases, they only require a subset of this code. For instance, in the picture, this is a kind of standard and also security sensitive application of Bluetooth, in which you can think in a restaurant, for instance, where you have a credit card reader. This is from Square. So you have a Square credit card reader. You have, of course, a credit card that is you insert into the reader, and then the reader communicates through Bluetooth with an Android phone and with the Android app, the Square Android app running on that phone. So, and this is used to do payments, like in restaurants or bars. And this sort of application, it only requires a subset of the Bluetooth protocol. In particular, in this case, we just need the GATT profile, and we just need a few protocols, and all of this is only going to generate a few HCI commands that are only triggering some specific parts of the code running in the Bluetooth controller. So it's obvious that what we can do here is to identify these areas of the code that we need and remove everything that we don't need. And why do we want to do this? We want to do this because by removing the unneeded code, we can make these Bluetooth stacks in a way immune to attacks affecting other components. No? So here, maybe there are bugs in this profile in this BNAP protocol, but if we remove all this code and we only focus on the code that we need to run our Square credit card readers, that device that is doing something sensitive, that is reading credit cards, so could potentially be attacked to steal credit cards, at that point, that device becomes immune because it just simply doesn't have the vulnerable code. So this is the general idea of debloating code that is applied to the Bluetooth protocol. So starting from all these observations, we wanted to create an automated system to debloat the code. No? And so the system that we designed that is called LightBlue needs to be automated, needs to be flexible because many different devices, they use different implementations of Bluetooth, different operating systems, they use different implementations of Bluetooth, and we want to debloat both the code running in your operating system, what we call the host code, and the firmware, the code running on your dedicated Bluetooth CPU. So in summary, LightBlue works in 3 steps. So first of all, we start from an Android applications and we identify the profiles that are needed by these applications. Then starting from this profile, we identify the protocols and the pieces of code within the host code that are needed by this profile. Then we identify the commands that are used by the host code to communicate with the firmware. And by identifying these commands, only the subset of commands that we need, then we can go into the firmware and remove all the handlers that are dealing with commands that we don't need. And so we can also debloat the firmware. That is the third step. Okay, so just going a little bit more technical here. So to identify which profile a specific app is using, we can check how some specific APIs are called. So for instance, this get profile proxy API on Android apps. So we can scan the Android market, finding apps that are using this specific API and identify how they're using this API and which profile they need. Then we need to go into the host code, and starting from a profile, we want to understand what is the code that is triggered. So to do this, we need to do a kind of per profile analysis. And to do this analysis, we need to basically do a reachability analysis in which we start from a profile, and we want to understand all the code that is potentially reachable by that profile, so that we can remove the other code. So to do this is we kind of use a mix of two techniques. One is a control flow analysis, in which we see how the execution flows within the code, and the other is data flow analysis, in which we see how the data flows within the code. And one particular, there are basically two challenges in applying these techniques to Bluetooth host code. One is that sometimes we need to be able, given a specific profile that we want to keep, what are the values that specific variables can take? Because the code contains a lot of this sort of switch cases in which, given the service ID that is the profile, different code is executed. So we need to know that since we want to preserve a specific profile, then service ID will have a specific value, and so this case will be executed and this function will be executed. So we need to understand these automatically. And also the host code, it works kind of in a callback way, in which it contains multiple multiple entry points, some for initializing the protocol, some from using the protocols. So we need to simulate in our analysis how the execution flows from initializing functions, usage function, and termination functions. So after we do this, we're able to identify all the pieces of code that we want to preserve, given a specific functionality of Bluetooth that we are interested in. But we are also able to identify the commands that we call the HCI commands that this functionality sends to the firmware. So now we also know the commands that we need, that this functionality sends to the firmware, and so we know the commands that we want to preserve into the firmware, and we can remove the others. So to remove the others, we need to understand where the commands that we want to remove are implemented. Specifically, these are implemented to handlers. So what we want to do is to identify in the firmware code automatically where is the code parsing these commands and determining which type of commands they are, and then dispatching them to the different command type handlers. So these analyses, we design a way to identify automatically in firmware where this sort of dispatching functions are. And this is particularly challenging because firmware is not open source. So we need to do a binary level analysis. And without going to the details, basically the analysis is based on the fact that since a command has a specific structure, the code that is parsing it needs to have a specific structure. So by doing binary analysis, we are able to identify code that is parsing data with that specific structure. And so we implemented all of this using an LVM for the host code analysis, because we have source code of the host code. Whereas for the firmware, we use Anger, and that is a binary analysis tool, because we don't have a source code for the firmware. We try all these approach on 4 different host code running on different Android devices, running on different embedded systems, and on different firmware samples. So what we can see is that on average, by keeping one profile and removing all the others, so while keeping one functionality and removing all the other code, we were able to reduce the code by about 40%. And in the firmware, we were able to remove most of the HCI command handlers, because this firmware implements a lot of what we call vendor-specific commands, a lot of commands that are only used for debug or for development that are potentially vulnerable, but they're typically not used in normal Bluetooth operations. So we also remove a lot of them. And after doing this, we were able to significantly make the firmware and the host code safer. No? So this is a list of CVE, a list of known attacks that in our debloated firmware and in our debloated host code, an attacker cannot do anymore because we just removed the code that was vulnerable to these attacks. So this is a list, and some of these could even be triggered over the air. So without requiring the user doing anything, just by getting near to a Bluetooth-enabled device, you could trigger these attacks. If you don't, but you cannot trigger them anymore in our debloated code. So I'm just going to show you a demo here, just to show a little bit more concretely. So here we are running, you can see on the bottom left, you can see a Nexus 5 phone, and in this phone, and here on the right, we are running a script that is triggering an exploit against the phone. So now we run the exploit, and we will see that the Bluetooth crashes. Should be now. Okay, so we see that Bluetooth crash. So then what we can do is that we can run our debloating code. I'm gonna skip some part, but first of all, we analyze the square up. We identify that the square up only needs the gut profile. Then we run our LLVM analysis, and our LLVM analysis will generate two things. One is the debloated host code, and one is the list of HCI commands that are needed. So after this, we take this information, and we first of all we need to flash the new host code into the device, because the debloated host code, we need to put it into the device, and that we are doing it right now. And then we also need to debloat the firmware. So to debloat the firmware, we start from the list of HCI commands that we want to preserve, and then we just run the script to rewrite the code in the firmware. And after we do all of that, we can see two things. So we want to verify two things. One is that the phone is not vulnerable anymore to the exploits that we ran before. And here you can see that the script is unable to trigger the exploit now. So this shows that the phone is not vulnerable anymore to that attack. But in a sense, but in parallel, we can also show that even if we remove a lot of the Bluetooth code, we can still use the functionality that we are interested in. Specifically, we can still interact with this Square credit card reader. We can still connect to it and potentially use it to accept payments. So again, even if we debloated the Bluetooth stack, the device that we are interested in, this credit card reader, is still working as intended. And so we have a safer device, a safer phone, a safer connection that is still working for what we want to do. And this is the end of the demo. And in summary, we developed a technique to identify unneeded code in the Bluetooth stack and remove it through an automated debloating approach. We were able to remove about 40% of the host code and about 60% of the firmware. But most importantly, by debloating the code, we were able to make the Bluetooth stacks immune to 20 known attacks. And of course, and this has been published in a recent paper. And also the code is all public on GitHub. Okay. Maybe we have a few minutes for questions, or I'm not sure.
Wonderful. Antonio, thank you very much for presenting your research. To everyone, I have linked to Antonio's homepage in the chat. Please feel free to follow up directly. Also take a look at some of the white papers for some of his other research. Again, Antonio, thank you very much for presenting.